What is this setup? There's like a
laptop and a projector and
so there are actually people. I'm a little bit afraid. I see so many people so close to each other not wearing masks.
Yeah.
Yeah, I didn't decide.
It's like here.
Okay.
I realize now when I watch television and they have like people talking to each other, like from TV series or films shot a year ago or more, a bit over a year ago, and it's always like, oh wow, what are they doing? Yeah.
Do you hear us now?
Yeah, that's the right microphone now. That's pretty good.
Great, we hear you also very well. We have you on the speaker, so that's great. Okay, so I guess without further ado, we could start our April monthly machine learning seminar. So welcome everyone. I'm Katarina. I guess most of you know me. Lecturer in the machine learning group at University of Auckland. And today we have a guest from Europe, actually Finland. You are for the first time in our machine learning seminar, Pauli, and he will talk about hyperbolic communities, modeling clique communities with tropical algebra. But before we continue and give you the chance to present your work, Jörg will introduce you shortly.
Yes, I heard that today. So yes, thanks, Pauli, for joining us. Pauli is a professor for data science at the University of Eastern Finland in the School of Computer Science. Before that, he was senior researcher at the Max Planck Institute for Computer Science in Saarbrücken in Germany. And at the moment, he's also adjunct professor at the University of Helsinki. His PhD he did a few years ago at the University of Helsinki, and he always published a lot of papers on Boolean matrix factorization. That's a connection both of us have. And in general, his research is algorithmic data analysis. He has quite a few publications. Just checked it. It's 96 publications on Google Scholar with more than 1,300 citations. And yes, thanks a lot for joining us this morning or evening. And sorry that we give you anxiety by sitting close to each other. But don't worry, you're in your room alone. So feel free. Take it.
Thank you. Thank you, Jörg. And yeah, indeed, as Jörg said, I used to be in Germany at NPR Inf, and what actually I'm presenting here is sort of culmination of the 8 years I spent at NPR Inf. And at the end of just before I moved here to Finland a couple of years ago, I sort of realized that most everything I did while I was in NPI was just a single topic. So before that, I thought I'm working in 3 different topics. But on like one morning when I was having a shower, it occurred to me that actually I am not working in 3 different topics. I am working a single topic. I'm not entirely certain. I have a feeling it was a good thing in general, but yeah, it's not clear. And because it's this kind of old work with so many people, or work of so long time also, this is a joint work with lots of people. So Sanja and Saskia were my PhD students back there. They're now both graduated and went to industry. Stefan Neumann did his master's thesis with me in Saarbrücken, but then left to Vienna and graduated, got his PhD from there, and is now in Sweden in Royal Technical Institute. Heine Gemula was actually with me in NPI Inf. We're together senior researchers, but now he's a professor in Mannheim. And Stefan Günnemann was in fact the only person who was not there. He was in Garnic Mellon when we started this. But then he moved to Germany and is now in Munich. And there's an empty spot of some future collaborations. I can use the same slides in 5 years and still put more collaborators. And I'm going to start, and most of the talk is going to be about the communities and the graph mining. And I hope I still have time to discuss more about the matrix factorization stuff that Jörg is waiting eagerly. that we get into that, but I'm very sorry. It's kind of like it's the last topic, so depending on how long I spend on the other, I might have to rush it a little bit. It could be a talk or a lecture, or I think actually would be a course of its own if I would want to go through the whole thing, but I try to give you at least some intro on there. But we start with the graphs and with community mining. So typically when you do community mining, you think that the community is some kind of a quasi-clique. Most literature considers a community in a graph is a quasi-clique. So essentially, it's a group of, in the human case, it's a group of people who all know each other, or at least most of them knows each other. And if some people don't know each other, so there is an edge missing, this is essentially a uniformly random occasion. So all edges are equally likely to be present in a community, and they should have a higher likelihood to be present than outside the community. That's the typical model. And what you see on the right, and I'm going to use this kind of plots a lot here, is basically an adjacency matrix of a graph, where these orange dots mean that there is an edge between node 200 and here node 50 something. This would mean there is a dot there. So now if this is a community, if this is a clique, this is actually a one real world community out from one network, where we just took the subgraph of this corresponding to this community. And based on the assumption that this would be a clique, a quasi-clique, obviously it's not a clique. If this would be a clique, this would be like all orange, solid orange. But the assumption that this would be a quasi-clique then basically means that this should be approximately equally dense everywhere. Now, okay, we see it's not entirely so. There is kind of like few denser things, but it's not entirely unreasonable from just looking at this plot. Now, however, if I do something, if I reorder the rows and columns, this being an undirected graph, this is obviously a symmetric thing. So if I reorder rows, I need to reorder the columns. So if I reorder the rows just based on the degree of the node, in other words, the number of ones, I see this is absolutely not symmetric, or this is not like a uniformly dense area. There is clearly somehow denser area here, here, and then there's an extremely sparse area here. So in the case of the quasi-clique assumption, you would assume that, okay, you see something like that, but it should not be like this. So there should not be like basically completely empty area here. So this empty area here, essentially empty area here, means that there's lots of people in this community who don't know each other, or who have no connection with each other, whatever is the definition of a connection in this graph. Whereas then there is this group of people here who know basically everybody else who is on the community, and who know especially each other. There is this, so this is a clique or quasi-clique essentially here, and then there's lots of people who just are not here. So just at looking this plot as a proof by a picture, I would argue that a clique is actually not a good model, and you have to trust me that this is not the only case where a community looks like this. We actually started looking at them, and when we started this project, we started looking at lots of communities, and turns out that very few of them actually look like cliques when you start looking at them. And well, okay, if you don't trust me, here is communities from Stack Exchange. I assume you all know the web page, a collection of web pages, where basically we take each of those stacks as one community, and the nodes are the users, and edges are comments or answers during the last year. So if somebody has commented somebody's question, or somebody's answer, or answer to somebody's question, then there is an edge between these two people. And these are 160, approximately 160 of them. And so I just plot them all here in this video. And yeah, you can see there isn't really that many that would look equally dense. after this, or uniformly dense after this reordering, and actually some of them are extremely biased towards the bottom left. Right, I let that roll and get on. So why should I care? I mean, come on. Well, one reason is that if we want to actually fit our communities into real world data, our communities should look like the communities in the real world data. I guess that's kind of like goes without saying. Now, if we can also understand this, we can have a better prediction. For example, you use these communities are often used in link prediction, where you want to predict where the link should come. So now if you typically assume that, okay, community should slowly fill in, so all those missing edges should be added there. Now, if you assume your community is a click, then you start assuming there should be lots of those edges coming onto that area, which is now completely empty. But I don't think there is any reason for that to happen. I think where you can still assume the edges to come is there at the bottom left, if something is missing there, but that top right corner, which is essentially empty, might really not start getting any more edges. So simply predicting the new edges, you need better models for the communities. Also, if you want to make random graphs, typical random graphs nowadays, if you want to model the community structure in your random graph, then you model a click-like structure. But if communities are not clicks, then of course your random graphs don't really look like real-world graphs, and so on and so forth. Now, we are not the first to claim that communities are not clicks. This, I think, the best known example comes from Bocatti and Everett from 1999, where they proposed this so-called core periphery model, where they say that, okay, communities have this kind of like L-shaped shape, where there is a group of people here that's called the core. So these are people who basically know each other. That's a clique. And then there is a periphery, which is the rest of the people, and they are connected to the core, so they know the core people, but they don't know each other. So this area here is empty. And so now, I'm sorry, this matrix that I got from their paper is drawn like as a mirror image of how I draw my matrices, but I guess you can do the mirroring yourself. So my core comes to the bottom left, and they draw it at the top left, but fine. And this is the sort of theoretical case, and of course in the real world case you would assume that there can be fused zeros, of course both in the core and in the periphery. So and some ones here in this area, but in theory the pure model is should like this. And they validated this with a quite famous dataset called the widow dataset. So they collected widows. I truly hope that they only asked afterwards and didn't kind of like create them, and then followed on how they make friends each other and what kind of communities form. And this is well, this is 1999 big data that you can still print in your paper, and then they could see that actually very much happened what their model was predicting. Except that not quite, because if you look at here, you see that there is lots of emptiness here in the periphery. So in this Bocatti and Everett's model, the periphery, everybody on the periphery knows everybody on the core. And I'm not quite sure that actually is the case. If you start looking at that, there are these people here, like this Khan and AMH, who know actually only very few people, or IJSW, whereas there's other people in the periphery, like this SWRA, who actually knows kind of like everybody on the core. Now, I'm not entirely satisfied with this model. I think it's a good step towards it, but I'm not entirely satisfied. So then there is another model. This is actually a model that comes from my PhD studies, or that was studied a lot back when I did my PhD studies in Helsinki, together with Professor Heikki Mannila. So nested matrices. A matrix, a binary matrix, is nested if its rows and its columns can be ordered so that all ones are consecutive and no row has more ones than the row above it. So you get this kind of like staircase pattern here. Now black would mean 1 and white means 0. And so you get this kind of like a staircase pattern here. And these are important kind of matrices in ecology. For if this is like a presence absence matrix, you try to find this kind of nestedness structures, and some of my former colleagues have used this to model fossil findings in paleontology and so on and so forth. Now, for this talk, what's important is that the core periphery matrix is actually a special case of a nested matrix. A core periphery matrix is something where the nestedness has this kind of like very simple structure, so it looks like that, but that still is a nested matrix. So the nested matrices give us a generalization of what would be this core periphery model, but actually rate a very general generalization. As you can see, like almost any kind of, well, not any kind of matrix, but they can look very interesting indeed. Now, third model that is like proposing something similar is the HyCom model that comes from Christos Phalotzos's group from Carnegie Mellon, 2014. They have this kind of same idea that, okay, if you sort your nodes by the degree, then you get this kind of plot that looks very familiar to you, like what I showed to you. And then you say that there is an edge between, I assign a number to my nodes in the order I put them. And I say that there is an edge between two nodes if between node A and node J, if I to the power of alpha times J to the power of alpha is larger than some tau for some negative alpha and some tau between 0 and 1. So there is this kind of like a power law shape here. And they study this. Now, what's important here is it looks like that you have an alpha here and you have a tau here, so you have 2 parameters, but actually you don't have 2 parameters because you can always just take the alpha root of everything and then just like say that it's just I times J and adjust your boundary condition, the tau thing. So basically this is like a one free variable. You fix the shape and then you can just change where on the on this thing you take draw the line, essentially. So that's what they proposed. And now if we look at these different models, the core periphery model, as I showed to you, it seems a little bit too restricted. It does not take into account the fact that the tails taper towards the end. They fade out. On the other hand, the nested model is extremely general and it's perhaps too general. Obviously, it can be used to model all of these other things, but it might end up overfitting to lots of the shapes in the communities. The HyCom seems like a good compromise, but it still is a little bit limited because it basically only has a single free variable. So what we propose is this hyperbolic model, where we say that, okay, there is an edge, like in the HyCom model, there is an edge between a node I and node J if I plus P times J plus P is less than some theta. So we draw a hyperbola here with the center at minus P, and then the theta says that where on this gradient we put the cutoff point. Alternatively, we also proposed a core tail model where we say that, okay, a community consists of a core, which is a clique of size gamma, and then this kind of like tapering of tail, which at the end of the community has height h, and it has the shape like drawn here. So there is a gamma, which is a clique, and then there is this kind of like a tapering of thing that ends up the tail, which thing thickness h. And obviously the thickness of h cannot be higher than the gamma, and so on and so forth. And in addition, we also proposed a third model, because when we got started with this, we thought that, okay, why not just get on with these models, which takes the HiCom model, which is this I times j is less than tau model here, and then a simple line, which just says I plus j is less than some sigma. So you just basically draw a straight line here, somewhere here, and we mix it. We just take a linear mixture of these two models. So we say that our final model is 1 minus x times I times j plus x times I plus j. So now when we vary the x, we get from a straight line into the pure HiCom model. Now, thinking that, okay, what you can see, what happens is that we can change the shape of the curve along the way from this kind of like a steep power law kind of thing into a shallower and shallower until it's just a straight line. Okay. I'll skip that slightly more general thing. First thing is that the three models I just proposed are actually all the same model. They're just parameterized differently, essentially. So saying that the community can be defined as this hyperbola function is the same thing as saying that this core tail, how we exactly defined it. I went over the definition there for the interest of time. That's the same thing. I just reparameterized my model, and that's the same thing as the mixture model, just again reparameterizing the thing. So what this basically means is that if I have a valid community in our hyperbolic model, I can just compute equivalent parameters for those other two models. And I can happily just pick up whatever of this model is most convenient for me to work with it, and change to another model, whatever is the most convenient for me to analyze. And for me, the most convenient is the core tail. I think the core and the tail, the size of the core and the size of the tail are the most intuitive parameters here. But for the algorithms, might be easier to, for example, use the linear model or something. Compare this model to the other two. So for the click model, well, the clicks are a special case of our hyperbolic model. So the standard ID, so we just basically set this boundary point, the theta, so high that the entire community is just its core, and that's it. Or in the core tail model, we say the size of the core is the entire community. So that's quite clear. The core periphery model, it's sort of like a limit case when we make the function so sharp that it turns into this core periphery model, but there's a limit case as the size of the community increases infinitely. So in practice, we can't quite force our model into this kind of straight lines, but we can get arbitrarily close to it. And then compared to the HiCom model, HiCom is just a special case that you can see from the fact that we use this mixture model. So HiCom model is the case where we keep only consider the HiCom shape and not consider the linear part at all. Right. So then, there's a couple of example communities just to show how rich our model is. So now if you're wondering, we're wondering what is that green line that I draw in my plot, so that's actually is the community I fitted into these things. So we see that we have this kind of essentially star-shaped communities, meaning there's very, very small core, only few people who then know everybody else, and then nobody else knows anybody, or very few of the others know each other. There is more of the kind of like HiCom communities that I discussed. There's basically cliques. I mean, some communities are cliques we can handle. There's this kind of like, it's not entirely clear where you should draw the line, but somewhere here, much more gradual change and this kind of like straight line in here. And also this line, there's more clear that the line should be somewhere here, but it's very, very straight compared to this plot here, for example. So all these different shapes we can model, which we thought is pretty cool. That is when you have just a single community. When we have more than one community, things get significantly more complicated in case they overlap. If they don't overlap, it's pretty straightforward. I mean, every non-overlapping community gets modeled independently, and then we just take the space between the communities as the same as the space that goes into this void here. So basically, there's a big difference compared to standard model. Standard model, when you know the nodes, so in the quasi-clique model, when you know the nodes that participate in the community, you know all the edges that also are part of the community, because they're just the edges between these nodes. Whereas in our model and in the core periphery and in the HiCom model, these edges here in the top right corner are not considered to be part of the community. So we have to separate between the nodes that are in the community and the edges that are in the community. And not every edge between the nodes in the community actually are part of the community. We say only these edges below the green line are part of the community, and rest is essentially some kind of a noise in this model. So if the communities are non-overlapping, we just consider this the space between communities be part of it. If the communities are overlapping, then we have a problem. Because, well, here's an example of a good community. And here's an example of another good community, which could be positioned like this. Both of these are independently rather good communities, but jointly they are quite bad communities because you see now this area here, which should be empty based on our model, is actually not at all empty, but there is this other community. So we have to somehow say that, okay, well, these edges that are between the nodes that belong both of these communities, actually these edges only belong to one of these communities. This could still be doable, but in real world, it can be like this. In which case we have edges that should belong to both communities and edges that should belong only to one community, and it just gets a big mess. And we don't have a complete solution to this, but towards the end of the talk, I will get into how I think I'm going to approach this problem. But for now, I'll stick to the case where the communities are separate and show you what we can do with the model in this case. And then, as I said, towards the end, I still have some time, I'll discuss how we can get into handling these overlapping communities and finding the communities. So one thing here is that for now, I'm talking about non-overlapping communities that have been given to us somehow, and just fitting our model into the community. So we are given the nodes that belong to the community, and we want to fit our model. Well, we can do the fitting. There's an optimal algorithm to do that. It's not too hard. And now what we're doing is we're analyzing what we get out of that. And at the end, I'll then discuss how we can perhaps find the communities. So the first thing we did, we just tested, is this any better than the standard clique model or the HiCom model? Here's the likelihood ratio. So when these are positive, we are better. There's only one data set, this is the DPLB data set, where this was not the case. I'll get to that in a second. Then we also, these are like given communities from the Jure-Leškovec SNAP data collection. Then we used some algorithms, including the Boolean matrix factorization, to find communities from the graph and then like remodel communities back, like put our model into those communities and compared how much better our communities are compared to those communities those algorithms actually originally found. And turns out that we are still better, even like if we use HiCom to find communities, and then we fit our model into those communities and then compare our refitted model better than the original HiCom model, we still beat. And the likelihood ratio test takes into account the fact that we have more degrees of freedom. So that's why we were using it here. But this is something I really wanted to talk about. It's what we can do with our model is that we get a great understanding about the shape of the community. So we can just look at the distribution of these parameters after we fitted the communities. Here, for example, is the core size relative to the community size. So if the core size is relative to community size is 1, meaning the whole community is a core, it means we have a clique. And if the core size relative to community size is extremely small, it basically means we have a star, saying there is only 1 or 2 members of the community and everybody else is connected to them, but not to each other. And between that, we have everything, like we have from star into a clique. And now just fitting these models into the communities and looking at these distributions, we see that, okay, DPLP is, or this a subset of DPLP is this DPLP 100. This is actually a clique. And this makes me wonder whether this is the reason why everybody always claims the communities are cliques, that they just be looking at this DPLP data set and saying that, hey, look, they look like cliques. But then if you look like the live journal here, for example, it's very much not a clique-like. So output data set here, the median is, it has a really long tail, but the median is really, really super slow though. So almost all of half of the communities are essentially star-like things. Amazon is slightly different, as is the DPLP and Friendster, and YouTube again is much more star-like. So this already gives us a much more of understanding about the shape of the communities here. And similarly, we can look at how thick the tail is. Like in the live journal, the tail is basically non-existent. In Amazon, it's much more varying. And then we can look at how similar to the HiCom model we are. The HiCom model would be at the 1/2 here. Then you can see that, okay, actually HiCom, we definitely are not like how HiCom. So again, enforcing the fact that our slightly more general model really yields different results than just the HiCom. The next thing we did was that we thought that would be great if we could now predict the change of the shape of the community as time goes on. So we thought we're going to write a cool paper where we are going to take evolving graph and then a cool algorithm that's able to say that how is the shape of the community going to change as the graph evolves. And for that, we went to the Stack Exchange data again, where you can get the change over time. We took it, I think, every month or something like that. Like people who commented or answered, or put an edge if there was a comment to an answer, or an answer to a comment to a question, or an answer to a question. We put an edge there, and we tried like take every month and sliding averages and so on and so forth, sliding windows and so on and so forth. And we started looking at how does it look like over time. And we had to abandon our cool idea of this great paper, because it turned out that the relative core size, so the core size relative to the community size over time, this is from January 2011 to somewhere end of 2016, is a flat line. So our initial idea actually was that, okay, this is going to give us like a really cool, really easy algorithm, and we're just going to beat everyone. We just figure out where is this flat line, and we're going to get like a 98% accuracy with a supremely simple algorithm. But then we started looking a little bit more of these. So what you can see from this plot is black. Black line is the size of the community at any given time point. The red line is the relative core size, so the core size relative to the community size. And the blue line, which you can barely see, is the relative tail size. So yeah, you see here it's first a little bit bigger, but then it basically flattens here, even though there is a bit of a variation on the community size. Then we try something else. Okay, so the math Stack Exchange grows pretty, these are from the Stack Exchange, so this grows pretty solidly, but then we look at something which doesn't grow so solidly and which is much smaller. Math is also, as you can see, this is the size, so it's times 10 to the power 4. So we look at gardening, which has this very strong seasonal fluctuation, quite understandably, and which also is very much smaller. So the number of people doing something there is just like 400 or 500 people, even at the best. But even though this line is not as smooth as it is on the math plot, simply because it's a relative size and there's much less people, so a single person coming and going will already start having an visible effect here. It still is there approximately approximately 0.1. And there is no clear trend going anywhere. And if we look at something where there's like a huge jump on the size, so the code golfing, which got super popular somewhere there between, I would say, end of 2013 compared to what it was. You can see this huge spike, but the fraction of the active people stays the same. Again, I mean, there's a bit more variation here when the community is smaller, but then there is no trend for this to going anywhere. And then we look at it at the different community services. So is this like a Stack Exchange specialty? We look at health boards. Also with health boards, we could see communities that are not only growing. Stack Exchange, everything is still growing. Health boards, we see this kind of a community that peaked there in 2007 approximately, and then started getting less and less popular. If you don't know what health boards is, then that might be the reason. But there you can see, but nothing changes, and it's there still around 0.1 at the relative size. And this actually, the Pareto principle you might have heard of, it says that 20% of people does 80% of the work. So first of all, we want to update this. It's approximately 10% of people who do most of the work. I don't know if it's 80% of something else. And this actually really turned out to be the case when we started looking at this in all of the communities. So on the left, you see Stack Exchange, all the Stack Exchange stacks. On the right are, I think, all the health boards. And you can see, if you can see anything, the red lines, almost each and every of them are very, very solid. Perhaps there's a bit of initial fluctuation when the community is very small, but then they fix there at 0.1. And so instead of getting into a cool computer science paper where we would have a really great prediction algorithm, I could still make this really great prediction algorithm. It would say that it's 0.1 and that's it. It gives me the size, I give you the size of the core. Size of the community, I give you the size of the core. But instead of making this kind of a paper, we went to sociologists, more like a sociologist, and we started saying that, okay, look, this seems to be the case, at least in this kind of community question answering sites. So where people need to work somehow altruistically to do things. So for example, answering questions in Stack Exchange gives you some virtual badge, but it can take quite a lot of effort. And it seems that it's pretty exactly 10% of the active users who really answer. Pretty exactly 10% of the users are active. And the remaining users are there mostly to ask questions or at most like answer a single question or something like that. But there's approximately 10%, and it's pretty solidly 10%, irrespective of the size of the community, that actively participates in these, which I think was pretty interesting finding on and in itself as an outcome of this work. Then, of course, there is a question that, okay, can we somehow explain this? And can we explain these fluctuations and so on? So we had a random graph model that can create now communities like this. And we can even model this cool fluctuation. So when the community size is small, which unfortunately here the colors changed. So the community size is still the black, but now the blue line is the real core size, and the red line is our sort of like a modeled average core size. And then this red shading gives us 2 times the standard deviation in the random graphs when we model these communities using our graphon model. And you can see that when the community size is small, so this works so that we give it the size of the community and the parameters, and then it randomly generates a new community drawing from, we give the distribution of the parameters and it randomly generates the community from there. And you can see when the community is very small, then also the core size fluctuates a lot. But as soon as the community starts growing, the core size in the random model also fixes. So it really is just a matter of essentially this kind of like a random distribution centering around its expected value as soon as you get more observations. So we also got our random graph model out of that, which I don't go any further so that I have some time to discuss about how to find the communities. So far, as I said, everything we've done, we were fitting this model that took its own algorithm. It's an interesting work of itself, but I'm not going to go into that. But we were fitting this into given communities. Now the question is, how do we find the communities? So we can use a click-like community finding algorithm and then remodel. So take the click and then put our model on top of what we found for the nodes, but this might not be very good because it's not finding correct shaped communities. Or we can first find the cores. So use the click to find the cores and then grow from there. But now the overlapping communities cause issues. So our answer to this gets back to this matrix factorization. And we started with these nested matrices because though they are a little bit more general, they were also easier to find. So our ID, actually it says work in progress here, but it's no more work in progress. It's now done. It's work that is no more in progress. So our ID is that we'll express the adjacency matrix of a graph as a union of nested submatrices, which is a bit more general than what we did, but which, as I said, we think is a little bit more general. And our ID is that we can find these nested subgraphs by finding a suitable matrix factorization. And for this, I need to discuss about two topics very briefly. So one is the problem of what kind of a matrix factorization should I do? Because what I want is that I want to find a collection of rank 1 matrices so that when I combine those rank 1 matrices, I'll get this, my original graph, and every rank 1 matrix is a nested matrix. The problem is that nested matrices are not rank 1 matrices. So what I need to do is I need to change what I mean by rank 1 matrix. And what I mean by it by now is that I mean that a matrix has a rounding rank 1 if I can express it as an outer product of two vectors after I apply a threshold operation into it, meaning that let's say all the values that are above 0.5 I turn into 1, all the values less than 0.5 I turn into 0. And I say it has a non-negative rounding rank if the x and y are non-negative vectors. And this result with Stefan Neumann we got in 2016 says that a matrix is a nested matrix if and only if it is a non-negative rounding rank matrix. It has a non-negative rounding rank 1. So nested matrices are exactly the matrices with this non-negative rounding rank 1. I'll show you an example. So this is a nested matrix. It's a binary matrix. And I can express it as an outer product of these two vectors. So 4, 2, 1, 1/2, 1/4, which gives this. I mean, this is not that, but if I round it anywhere between 1/2 and 1, so truncate it into 0, 1 matrix, I get my original matrix. So that's my idea now. I want to find these kind of vectors so that after I apply the rounding, I get my original communities now as a nested communities. The only problem is that this doesn't quite work like that. Because if I have this kind of a nested structure as a single vector, and then I have more than a single vector, and I first do my matrix multiplication and then the thresholding, it's quite possible I just broke the structure along the way, because it's possible that I have two values there which are both below the threshold. So if I would round my rank 1 matrices separately, I would get two nested matrices. But if I just sum up those two rank 1 matrices and then round, I start getting ones on a position that there were no ones originally. Because, you know, if I sum up two numbers that are less than some number, I might still get like a number which is above that threshold number. It's like a deep math going on in here. I understand that. So if we want this to work on a non-completely disjoint communities, we need something else. And this something else is what I was working with Sanya Karaev and what he did his PhD thesis for, and it's called Subtropical Algebras, which I originally started working as a generalization of a BMF, so a Boolean matrix factorization. And there the idea is that we have non-negative values. Our summation is the maximum operation, not the ordinal summation, and the product is the standard product. And now what happens is that our thresholding operation from the previous slide nicely distributes over the maximum operation. So if I have two values that are both below a threshold, then their maximum is also below a threshold. So there is actually nothing deep going on in there as such. But this now tells me how to find these nested communities that are potentially overlapping. It simply says that, okay, I want to find a non-negative matrix B such that this subtropical matrix product of the B with its own transpose thresholded into 0, 1, so rounded into a 0, 1 matrix is as close to my original 0, 1 matrix as possible. And now each of the rank 1 matrices that this matrix factorization here defines are nested matrices thanks to this non-negative rounding rank property of them. And it's the same thing, this whole operation is the same thing as considering those nested matrices independently and then taking their union to represent my original matrix. And yeah, we can get this working. We got this working, and we look what we get. We get this kind of hyperbolic communities that are a special case of the nestedness. We get this kind of like a communities where you can see it's like an almost hyperbolic. It's not quite hyperbolic, but sort of like a little bit more rugged than what we would get in our model, which is smoother here. And then we get this kind of like, because this is also a nested matrix in this setting, but it does not fit into our hyperbolic model at all. This shows it's a bit more general, and it's actually, in my opinion, probably too general. Now, the thing, which I don't have any slide for, is the future work, which is to use this ID to find the hyperbolic communities, which works roughly the same, except that I just need to start putting all kinds of constraints onto the how these matrices here can look like. So these matrices must have values that have a certain constraints. Actually, in Saskia's PhD thesis, if anybody is interested in the end, in the future work, she opens up a little bit how this shape should look like. There's kind of like an arithmetic progression you need to put there. But now it's time to end. It's 10 to, so I will end here. Thank you so much for listening. I actually don't know, maybe you just turned off the microphone. Jörg at least was sleeping, but that's fine. I guess it's late there.
My eyes were open.
Yeah, but your sleeping eyes open, I know.
Great, thanks for the talk. I forgot in your introduction you asked me to say that you're very charismatic and funny. Sorry. Anyway, any questions from any audience? If you have questions and you are remote, just raise your hand or something. I can let you unmute yourself, or from the room.
Okay, let's see. Any questions in the room? Yeah. No question. Okay, we have 2 questions. Peter, do you want to come closer?
All right, yeah. Do your formulations only work on a undirected kind of graph, or can they work?
Yes, this is only for undirected graphs. It's a great question what to do, which you didn't ask, but it's a great question that I think you were thinking about, what to do in case of directed graphs. But in the interest of time, I can only say that it gets significantly more messy, so we decided to not think it for now, but it's an interesting future work. But yes, thanks. That's a good question. I should have also mentioned it.
Okay. Can you pull up? Okay, Thomas?
Yeah, I was wondering, how is the likelihood ratio calculated you used to compare against, like in slide 20 or something like that?
Sorry?
I was wondering, in some slides around slide 20, I think you have like tables with a likelihood ratio, and I'm wondering how it's calculated.
So it's the standard likelihood ratio test when we have the. So I can find the slide even. I guess that was the slide you were talking. So we have the likelihoods from these models that say what's the likelihood of the graph given our models for the full graph. And then you can just use the standard likelihood ratio test where you compare these likelihoods and take into account the differences in the number of free parameters. So our model has basically 2 free parameters. The block model, so the click, has no free parameters because it says that as soon as you know the community, it's like it has to be all edges in, and the HiCom has 1 free parameter. So then you compare the ratios of the likelihoods, and then based on the difference of the number of free parameters, you get these from, I think, the chi-square distribution, the values. And then essentially the larger the ratio, the more likely our model is to be better. And there is these few cases in the left, you can see the DP, in case of the DPLP data, the 2 versions of it, where the other model was better, which either means that it's because it has less free parameters, so there's a better idea to use the simpler model, even though ours is a bit more accurate, but needs more free parameters, or then our model, which in case of non-overlapping communities is optimal, but in case of overlapping communities, which does happen with these data sets, if they're given to us, we need a heuristic to actually choose what to do. It might be that we made a mistake, or the heuristic was not optimum there. But for as you can see, for almost all of the cases, we actually beat quite handsomely the competition.
Thank you. There is one more question here.
So there are 2 parameters in your model, and I assume they are not pre-trained, they are not predefined, but training by fitting into the different communities. So can you introduce more about the training process of these 2 parameters?
Sorry, can you repeat the end?
I can rephrase. So the question was about the parameters and how do you tune them?
Yeah, so yeah, I skipped the part, how do we find them? So for every community, what should I show? Maybe this one. So basically, we can do the for if the communities are non-overlapping, we can simply do an exhaustive search of the parameter space. It's not even too expensive because there is only like a discrete steps in the community size that make any difference on the final size, and then the hike, the same thing with the tail size, and then there is this relationship between the core size and the tail size. So not every tail size is valid for the model. So if we have a non-overlapping communities, we can simply fit every community using this kind of exhaustive search. So get the parameters for this particular community correct. And in case we have an overlapping communities, then we have an iterative process where we fit these into the like every community separately, and then we start looking at what is the final thing and where to like update them based on what we have on the other ones, other communities. However, this iterative process is then of course a heuristic. So there we cannot guarantee that the final full graph model is optimal.
Thank you.
Okay. We have 2 questions online. One is probably easier to answer. Can we share the slides of the talk?
Yes, I guess I can send them to you, Jörg.
Yeah, I'll put them somewhere online. And the other one is from Nin. Do you want to ask him yourself, Nin? We don't hear anything.
Oh, hello. Can you hear me well?
Hello? Now I can, yeah.
Okay, that's great. Just a question about the capital motivation from the subtropical algebra, right? So, so what's actually capital motivation from the tropical algebra? There must be some link with the matrix factorization, right?
Yep. So why the subtropical in general? Why study such a weird beast? So the original motivation actually goes in operations research, because you can model certain kind of dependency graph systems with this kind of subtropical algebra. So if you have a process where like some workers need to first work, and then other workers need the results of the previous workers before they can start, and then they need to be finished before the next layer of the workers can start. You can model that as a subtropically linear or tropically linear system to find the optimal solution. So that's why mathematicians and operation research people have studied it before we even started. My original motivation was that I was looking for doing something different than just zeros and ones, and wanted to get some smoothness in my optimization functions, and thought that, okay, maybe this could be an interesting approach to get, like, because if you think of it, Jörg will hopefully recognize it quite quickly that what happens here here is basically, if all the values are zeros and ones, then this is the Boolean algebra. And so this is basically a relaxation of the Boolean algebra in the case of the non-negative values, it's like relaxation of the Boolean algebra to the non-negative numbers. So that was my original motivation. This is what I was doing with Sanja. I told you that I thought I was working on different topics. I was working on the rounding rank with Stefan Neumann and Rainer Gemuller. I was working with Sanja on this subtropical algebras, and I was working with Saskia and Stefan Günnemann on this graph stuff. And then not much before I moved back to Finland, I one morning woke up and just, like, to my utmost horror, I realized that I've actually not worked on 3 different topics, but I've only worked on a single topic all these 8 years, just that I never knew about it. No, actually, I thought it was really great because now I have a clear ideas also how to take all of these things forward.
Do you have any kind of feeling about the relationship with any operation in the finite field, like in the GF2?
No, so the idea is that in GF2, that's the thing, these are fields, whereas subtropical algebra and Boolean algebra are sigma rings. So the most important feature here is they are anti-negative. So we don't have this subtraction operation available for us at all. Also, they're idempotent, so that, like, A plus A equals A. So that sort of makes them a very different beast than fields, finite or infinite.
Yeah, okay, thank you, I got it. Thanks a lot.
Okay, good.
I'm just aware of the time, and you told me earlier that you have to run to.
Yeah, I will
right
unfortunately have to jump to see presentations from our students here. It's like 10 a.m. and they've slowly waken up, and they need to start presenting their master's thesis studies. The 1st of May is approaching, and I don't know how it is in New Zealand, but in Finland the students tend to get wasted on the 1st of May. So better to give their presentations now. Next week they probably won't be able.
I'm sure our students don't drink and work all the time. Thanks a lot for giving the talk. Any comments from
No, thank you. Yeah. Also, it's exciting and it's interesting to see. I kind of like that 10% that you discovered. It kind of reminds me of another golden number or ratio that you have found. I'm just curious how applicable this is to different types of networks, like, for example, that come from biology in particular. That also the case, but I guess that will be left for another occasion to discuss.
Yeah.
I'm sure Pauli will come visit us one day once he's allowed again.
Thank you.
Good.
Thanks.
Thank you all for coming or joining via Zoom. Yeah.
Thank you. Thank you for inviting me. Maybe one day the traveling reconvenes and I can actually visit you in person.
And don't worry, we will show up.
Good. And in the meantime, Jörg owes me a couple of favors, so.
Okay. Thanks, Pauli.
Thank you.
See you.
Bye.
Bye.
See you.